This is the IEEE Computer Society Distinguished Lecturer Webinar Series brought to you by the Distinguished Visitors Program. The Distinguished Visitors Program delivers tools for individuals at all stages of their professional careers through visits to chapters, offering opportunities for individual interactions, and to the membership through webinars by respected professionals. We have distinguished visitors around the world who cover machine learning, cybersecurity, robotics, big data, cloud computing, blockchain, and cryptography, among others. Chapters can request a distinguished visitor on computer.org/distinguished-visitors. The Distinguished Visitors Program is able to pay up to $1,000 for a visit to a chapter, but by working with other nearby chapters to develop a tour, that amount can be increased. So when your chapter is planning its next event, think of the Distinguished Visitors Program.
Well, good morning, everyone. I hope you can hear me okay. I was pausing. I didn't know if the IEEE people wanted to do an introduction first or if we just got started, but I guess we just get started. I'm trying to see if everyone can hear me. I'm looking in the Q&A. If someone
yes,
could
we
just
can hear you.
Okay, can the attendees hear me? I'm seeing one person saying they can't hear the speaker. They're saying they can only hear the keyboard.
I accidentally put myself on mute.
Okay, so I'm getting several people in the Q&A saying they can't hear. Now I'm getting one saying they can't.
They're just a little behind us.
Okay, if everyone can hear, we'll go ahead and get started. First of all, this is obviously a very broad topic. And I know from looking at not only the attendees, but some emails I received in advance, that we get people from a broad range of engineering disciplines. So what is it we're going to hopefully accomplish today? Well, undoubtedly, particularly for several of you that I've heard from, there'll be some things you're already familiar with because of your own breadth and depth of engineering. But hopefully we'll be able to give you some new perspectives. We can give you some new areas you might not have considered, but obviously we'll be covering a few things that you have heard of. But what will undoubtedly happen is something you've heard of, someone else hasn't. And hopefully we'll give you some new perspectives on these topics. They're very interesting topics, and frankly, they impact almost every area of engineering. I say almost because there's always going to be some discipline I haven't contemplated, but in all honesty, everything I have contemplated is impacted by these three topics. So let's begin with defining what we mean by these topics of complexity and emergence and later chaos. What exactly are we talking about? Let's start with some terms, and these are meant to be generally applicable terms that will apply. I don't care if you're an electrical engineer, an aerospace engineer, nuclear engineer, or whatever the case may be. What is complexity? Well, let's first start by talking about order and chaos. Order is usually self-evident. There are a lot of different ways to define order. Some people will say a system with zero entropy. Well, that's probably a little extreme. I've seen that in some textbooks, but that's going to be a little extreme. You don't have to have zero entropy to have order. One of the definitions I really like are the elements of the system are at some sort of definable regular sequence. In essence, order is when we can define some level of structure either in the construct or the interactions of a system. Now, chaos has a lot of definitions and a lot of implications. One of the most widely read books on complexity by Strogatz says chaos is aperiodic long-term behavior in a deterministic system that exhibits sensitive dependence on initial conditions. Well, that still isn't quite clear, at least to me. So let's give ourselves some definitions here that we can use at least as working definitions for the time we have together today. Order, we're going to define as any system wherein we can observe structure in either the construction or the behavior or the interaction of the system. Chaos, we're going to define as any system where the initial conditions are so sensitive that very minor changes in initial conditions can cause substantial changes in the later conditions. Now, let me put that a little bit more clearly. What we will see is that changes in the initial conditions are so substantial, even if you make a minor change, their impact is so substantial that after a period of time, we can no longer predict the system. We just don't know what's happening. Now, this takes us back to complexity. Complexity, obviously, how complex a system is to some extent a subjective determination. But in general, complexity is a system wherein the interaction becomes somewhat difficult to model and to understand. But the really interesting thing, at least in my opinion, from all of this becomes emergence. There are a lot of definitions of emergence. Now, someone is indicating they're getting lots of sound dropouts. If anyone else is having that, please tell me. Someone else is asking about a copy of the slides. I believe I was asked by IEEE if they could hand out a copy in PDF, and I said yes. So you should be getting a copy. And I'm getting a little feedback from someone else, so if anyone else is online with a microphone, please mute it. Now, back to complexity. When a system becomes so interactive that we have difficulty modeling it and understanding it, it can be defined as complex. And I'm still getting some feedback from someone, so please, if you are online with a microphone, please mute the microphone. Now, emergence is, again, in my opinion, the most interesting. We're going to look at a lot of definitions. It's a property of the whole system, not specific parts, so it can be considered as holistic. Now, this often occurs in systems where the behavior is important. In other words, if you simply have a very complex structure with very limited interaction, you're unlikely to see emergence. It's when the parts are interacting. Now, over the years, there have been several different types of definitions defined. Now, the Systems Engineering Body of Knowledge, or CBOC, actually defines 3. And one of my favorite books on this topic, Engineering Emergence, a Modeling and Simulation Approach, defines a 4th. So let's talk about these because they're going to be very important, and they're really the crux of what we're getting at. Simple emergence, I really wouldn't even call emergence, although some people do. It's simply looking at the combination of the elements of the system and the relationships. The reason I would not call it emergence is because it's entirely predictable. You can easily see the system. You expect it. The parts of an airplane, I put them together. I expect them to work in conjunction to create specific functionality and effects. There's nothing surprising there. Weak emergence is emergence that's predictable, but I may or may not have wanted it. For example, when you're an engineer and you're designing engines, excessive heat, particularly in braking systems, they're going to generate heat. Well, I didn't want that, but I understand it's going to occur, and I have to account for it. Where we get interesting are things like strong emergence. There are unexpected properties of the system that I was unable to predict. It was not anticipated during design or development. Now, in an engineering perspective, we're often going to see that when it comes to failures. Normally, from an engineering perspective, anything that we didn't plan for is not good. The whole concept of engineering, regardless of your discipline, is everything is carefully planned, carefully designed, modeled, and tested. We don't do things off the cuff. One of my pet peeves in the world comes from the world of IT, where everyone calls everything engineering, and I have a real problem with that. If you just sit down and start cranking out code, you're not a software engineer. You may be a programmer, but you're not an engineer. When you do careful planning, requirements, modeling, design, then you're an engineer. Well, if properties occur that we couldn't have accounted for or anticipating during design and development, we have strong emergence. Now, the previously mentioned book, Engineering Emergence, a Modeling and Simulation Approach, defines a fourth version that's not been defined by the systems engineering body of knowledge, but I kind of like the terminology they use, although it's untechnical. They use the term spooky emergence. They're saying that what's happening isn't even really consistent with the known properties and behaviors of the system. Now, as we'll see a little later, this can occur in a wide range of engineering systems. In most cases, it is something we don't want. However, we're going to see a few cases where it actually is something we want. And we'll see that it might actually be desired. So, now that we've looked at emergence, let's return to complexity. There is such a thing as organized versus disorganized complexity. Disorganized is more interesting from a point of view of failure analysis. Organized complexity is simply the fact that we have a complex system. We expected a high level of interaction between the various components. This is all anticipated. As early as 1948, Warren Weaver discussed disorganized complexity, and basically we have interaction between parts that are accidental. Unfortunately, in engineering, this almost always occurs because even our own system, as much as we might tightly control it, is going to have to interact with other systems. So we're always going to have this level of complexity. Now, all of this brings us to dynamical systems. You probably have an intuitive idea of this, and on the screen I give you a few very formal definitions. I don't usually just read screens to you, I give you discussion, so you can read these to you if you want a more formal definition, but let's look a little more operationally at dynamical systems. Let's begin with something that I'm sure everyone with an engineering degree is familiar with, basic differential equations, where we look at the evolution of a system in time. Now I pause occasionally because I'm looking at some of the questions. One person is commenting about systems interacting with humans. And yes, that's absolutely accurate. And human interaction brings another level of dynamics and complexity to our systems. And frankly, all of your systems have human interaction. You designed them for that purpose. So when we talk about dynamical systems, we're usually looking at differential equations of some type. Could be ordinary or partial differential equations, but the point is we're using some sort of time-dependent differential equation. Now, nonlinear dynamics is a subset of that. We have lots of different modes of response that could occur for the same identical parameters. You might have systems that are very sensitive to initial conditions. Now notice that when we talk nonlinear dynamics, we're actually talking about very similar topics to chaos. Now let me explain that now before we go any further. Technically, chaos is essentially nonlinear dynamics taken to a higher level, a more extreme level. In some cases, you might be able to predict for a period of time, but that quickly breaks down. And again, we're always going to be looking at differential equations. You're usually going to have some bifurcation point. Now, this simply means a point where something breaks off. It could be a doubling or quadrupling or a change. But that bifurcation is going to lead to differentiation in the system. If two parts bifurcate, then we're going to have two parts that go off in their own directions. Now, I'm seeing some questions in the Q&A. I will get to some of those in a few moments. Good questions. We're going to leave them for just a moment. The solution to the equation you see right there actually has three roots. And we also have attractors. We're going to talk a lot more about those in a second. Even in a totally nonlinear, chaotic system, there'll be attractors wherein the system tends to move towards those particular points. And those bring up a totally new aspect of nonlinear dynamics. Now, one of the questions I was just given in the Q&A a few moments ago is relating this to software. Could that be a case of strong emergence? Software in particular can be a very interesting place for nonlinear dynamics and chaos. And to answer the person's question directly before I go off on a bit of a tangent, would be yes. Software is by definition a system that's very prone to emergence and nonlinear dynamics for a couple of reasons. One of which is the number of different components you have to interact with. If you write an application for an Android phone, well, first of all, you have your application code. Then you have the Android code, which is based on its underlying Linux code that you're interacting with. Then you have a wide range of different hardware vendors it may run on, and that's another level of interaction. And then the aforementioned, one of your colleagues on this talk mentioned interacting with humans. You have human interaction, which is almost completely unpredictable. You put all of those features together. Even if the software was 100% perfectly engineered, followed every step of software engineering, you still have a high level of nonlinearity. And if we're going to be completely frank, much of software is not well engineered. It's simply coded, and that adds even more nonlinearity. So yes, you may have strong emergence that leads to vulnerabilities and flaws. Now, particular bifurcation we list here, and I don't know why I had the animations because I always just put them up at one time, is hops bifurcation. Now, it's not important that we delve deeply into each of these, and by the way, I should mention this now. We're going to mention a lot of things through here, and any one of which you may or may not have previous experience with. If you don't have previous experience, you might be saying, wow, why don't we delve deeper into that? Well, one reason is we have a limited time, but one of the goals of this sort of talk is to introduce you to lots of things that you can then dive into more depth later, such as hops bifurcation. My main reason for pointing it out is the year it was introduced, 1942. A lot of these concepts and a lot of the underlying math is not at all new, been around for many decades. It's becoming more interesting to engineers today because we're dealing with more complicated systems than we have ever dealt with before. And that issue is likely to increase, again, regardless of your particular engineering discipline. It's very likely that you're going to have increasingly complex systems, particularly as we start integrating machine learning into almost everything. We're introducing a new level of complexity. Now, nonlinear dynamics, if you want to look at a birthplace of it, is something I think definitely all electrical engineers have encountered before, the Lorenz equations. Now, I have to make a confession here that I always make at this point in these sorts of talks. If I didn't already know the outcome of the Lorenz equations, the implication, I probably would have had no interest. I'm just going to be frank. He began studying atmospheric convection. And I'm going to be, again, very honest with you, there's a reason I'm not a meteorologist. If I think about atmospheric convection, it doesn't excite my interest beyond what the weather is going to be like today when I exit my office. However, he was one of the first to document and to describe mathematically that very minor changes in initial conditions quickly over time lead to radically different outcomes. As a side note, there are a number of people who do study weather and meteorology in much more depth than I do that are of the opinion that we will never be able to do long-term weather prediction. and you've probably whether in your area prediction are often weak or more. You're on a compute office
Chuck, your sound has dropped out a little bit.
Nonlinear, be able to begin. He's experienced with several different things, but beginning with these specific parameters and a non-dimensional times to use a small table that are telling me that I'm cutting in and out. Now 3 people. Is that something? Am I being heard okay by people?
You were cutting out with me, but you're now back on, I think.
Okay, well, I do a lot of online stuff and even online teaching, so I tend to have a very, very good internet connection, so hopefully this will hold up for everyone. Several people are saying audio is breaking and sound is breaking. So let me pause again.
You're better now.
Okay, thank you. In any case, that is to give you a see now that very small differences, if you graph this out, lead to very big changes. Now, the point I was making when people started saying I was cutting out was this was originally written in Fortran, and it occurs to me that younger engineers may have never used Fortran or heard of it. Once upon a time, Fortran was the language for scientific and engineering programming. Now, some people are saying it's breaking up again. I'm getting no indication on my end of any internet connectivity issues. So I'm not sure what the issue is.
They are a little behind, so that may be part of the reason it's coming in a little bit late.
Okay, well, we'll just continue on and see how this works out. Now, again, we're trying
to resume. Is that right?
Sorry, my Google Home just answered something thinking I was talking to it, so let me turn that off. Again, we're trying to introduce you to a wide range of things. We're not going to be able to delve in depth into most of them, but these are things that if you haven't encountered before, you can further your knowledge of nonlinear dynamics. The Karamutu model assumes a very weak coupling among oscillators, but what it showed is the behavior of large sets of coupled oscillators in some cases start to synchronize. And this is emergent behavior. Now, one of the reasons to bring this out is to start bringing together these topics. Nonlinear dynamics, chaos theory, emergence, these are all interrelated. They're not separate topics. And unfortunately, some people view them as separate topics, and they shouldn't. Back to various models you can be concerned with, the KAM theory, called Mogarov-Arnold-Moser theorem, basically talks about very small perturbations in a dynamical system lead to lasting quasi-periodic orbits. In other words, very small changes can actually have long-term changes in the ultimate system. And again, we're just introducing you to various aspects of nonlinear dynamics here. Ergodic theory is another thing that you'll want to explore if you want to get more in depth into nonlinear systems. Basically, what happens in any dynamical system when we let it run for a long time? Unfortunately, if you want to study nonlinear dynamics and you're doing some sort of system modeling, no matter what you're using, if you only let the system run for a short period of time, you're not really going to see the full impact of the nonlinearity because some of these effects only emerge over time. Ergodicity is the concept that a dynamic system will eventually reach all the portions in its phase space it operates in. Brownian motion and diffusion are the most common examples. If you let the system go long enough, it will have reached every possibility in its phase space. So this is another aspect of nonlinear dynamics. We mentioned attractors before. One of the first attractors you will see in most textbooks on this topic are the Rössler Attractors. And basically, they looked at a chaotic system, and use specific values that you see on the screen there, and basically chaos only changes, and that really is the entire situation we're talking about when we talk about chaos and nonlinear dynamics. Tiny, tiny initial changes can lead to wide-ranging outcomes. Basically, and this is going to bring another mathematical recommendation to you. If you're a student, and I know we have some students that come to these talks, let me just go on another side tangent. Students often ask, and those of you that are faculty online may smile at this, students will often ask, what is the minimum amount of math that I must take in order to complete whatever degree? Well, that's an unfortunate question, because frankly, there's lots of math that you won't find an answer to or an application for until long later in your career. Right here, we're looking at a Jacobian matrix, which is often one way to describe Rössler attractors. Now, the point we're making is this. Someone is saying the audio is chaotic. I appreciate working that in. I don't know what the reason is. I know the IEEE people are looking into the platform to see if that's an issue. But back to the point at hand. Jacobian matrices are a part of linear algebra that are often not covered in the Introduction to Linear Algebra course. They're covered in more advanced courses. And frankly, most, particularly electrical engineering degrees, require linear algebra, and all too often students will take the introductory course and not go beyond it. I'm suggesting you go beyond it. Hénon maps are another way of looking at chaotic behavior. They basically look at a few parameters that can be seen in the formula above, and there are specific values in the classic Hénon map. I'm sorry, there were some humorous questions in the Q&A. Basically, changes in value will converge to a periodic orbit. Now, the reason to bring this up, and again, I mentioned that we're not going in depth into everything, is there's an odd issue with chaotic systems. As we saw with attractors and we're seeing with the Hénon maps, eventually what you're going to see is some chaotic systems have elements of convergence. Now, a question I've left on the table that's been in my Q&A box for a little while are, what are the best universities in the U.S. for nonlinear dynamics? Well, I don't know that there has been specific universities emerge. In certain topics, there are clearly a handful of top universities. I know the Santa Fe Institute in New Mexico is associated with several universities, and they do a lot of work in complexity. Several people have asked about the slides. These are being made available as PDF. I don't know how you get those. We'll have to talk about that towards the end. So we've laid the groundwork. What is chaos? Now, in 1972, Edward Lorenz, big name in this study, wrote a paper called Predictability. Does the flap of a butterfly's wings in Brazil set up a tornado in Texas? Now, that's how most people hear chaos, the butterfly wings. It's undetermined and undeterminable, if you ask me, whether or not that is literally true. But chaos is the essential idea that very minor changes in systems can propagate to major outcomes that we may not be able to predict. So that brings us to chaos theory and predictability. Physical systems can be classified several different ways. They can be deterministic, which we can clearly determine the outcomes. They can be stochastic and random. In other words, we get probability. The bottom line is, in chaotic systems, everything is probabilistic. And this has become more interesting in the past few years due to the widespread interest in quantum computing. At the quantum level, everything is probabilistic. Nothing is deterministic. So understanding probabilistic systems has become a lot more intriguing to a wider range of people. Lots of different mathematics have been applied to try to get a handle on the system. For example, using graph theory. And what you see here is a rather simplified graph. and we see the Hausdorff difference. Now, this is another area where I'm going to say too many times engineers and even mathematics students will take a discrete mathematics course that introduces them to graph theory, or maybe even an intro to graph theory course, and they'll stop there. And they won't encounter things like spectral graph theory and things of that nature that would give them a lot more mathematical tools. So one of the takeaways of today's talk, and for any of you that teach mathematics, you're going to love this, is you really can't take too much math. If you're a student, you can always take additional math. Squeeze in as much math as you can, not as little, as much. Now, what we're looking here on the screen with the Hausdorff distance and Hausdorff metric is basically trying to look at the complexity of systems by graphing the system, and the states of the system are the various vertices, and we want to know how far apart they get from each other later as the system evolves. Now, we've been talking about engineering, but this also applies to biology. Now, I know physicists and engineers like to chide biology as a soft science, and I'm going to make a confession. Once upon a time, I might have joined you in that. But one of the things I've discovered over the past few years of my career is there are elements of biology that are incredibly mathematically rigorous. And in fact, some really great math is being done by biologists, and it's worth exploring. In this case, they're looking at the coevolution of species and the fitness for a particular species in its environment. Now, why are we talking about biology? Because we see a lot of complexity, chaos, and nonlinear dynamics in mathematical biology. Someone asked earlier about code. Well, Halstead metrics look at computational complexity. How complex is the actual computation? Whether you're doing it on a computer or it's handwritten equations, we still have an issue of computational complexity. Now, probably the most important and fundamental mathematics related to chaos are Lyapunov mathematics. There's Lyapunov exponents, Lyapunov characteristics, and we'll see other Lyapunov inventions. Lyapunov did a lot of work in this area. And the Lyapunov exponent basically says, I have a dynamical system that began very, very closely tied. We had various parts of the system that started very close to each other. What occurs over time? How far does the system diverge? Let me put this in much more simple terms that are going to be very easy for everyone to understand. I'd like to know how chaotic my system is. Well, if I take a measure of the Lyapunov exponent over time, I'll be able to see how much it changes. Now, one person is saying the screen is not changing and he's still seeing the Lorenz equations. That is almost always a need to refresh on your end, because now you should be seeing Lyapunov exponents. Now, back to Lyapunov exponents, what he's measuring is the rate of separation of very close trajectories. So this will give you an idea of how chaotic the system is. Related to that is Lyapunov time. Now, there's a lot of ways we could describe this, but let's set aside the really, really heavy-duty math for a moment, and let's just make this simple. How far out can you predict a system? In other words, the more chaotic a system is, it will eventually reach a point that we've just got no idea. And I've given you a few estimates. Pluto's orbit, we can predict that out for 20 million years, so that's not a terribly chaotic system. Chemical oscillations, 5 or 6 minutes, we start to lose. Now, I'm getting some questions about the details of the Lyapunov equation. We're not going to delve into the exact specifics of every one of these formulas on the screen. This is a broad-based talk to introduce you to a lot of things, but I would say there's a lot of material out there. On Amazon, in fact, there's an entire book just on Lyapunov exponents. Weather systems are usually only predictable to 3 to 5 days. So that gives you an idea of the Lyapunov time. How far out can we do prediction before things just break down and we have no idea? Now, I had another question I was leaving unanswered for a little while. someone was asking about Feigenbaum constants. Basically, Feigenbaum was looking specifically at bifurcation and nonlinear maps. Basically, he's looking at the ratio of periods doubling. In other words, he gave you some insight into how quickly a system became nonlinear. That's another topic that we don't have in the slides, but I'm glad someone asked about it, because if you want to delve deeply into nonlinear dynamics, then bifurcation theory is definitely going to be an area you want to explore. Getting some interesting questions that we'll get back to later. Now, we've baked your brain a little bit so far. We've looked at a lot of different mathematical formulas, some of which obviously some of you are quite familiar with based on your questions, some of which may be new to you. But let's just look at this in a little different way. And by the way, the book I'm showing on the screen is a layman's book on emergence, easy for anyone to understand, very little math. And in that book, the author talks a great deal about emergence in biology. And I'll just give you one example. Harvester ants were deeply and intimately studied by entomologists, that's the study of insects, and they discovered some oddities. If you put together a huge glass enclosure and put in harvester ants, at a certain point, complex behavior emerges. Basically, if you have a few harvester ants, they just wander around with no direction. If you put enough harvester ants in a colony, we start seeing complex behavior emerge without centralized direction. In other words, contrary to what you might have seen in a Disney cartoon, the queen ant does not actually direct anything. She simply lays eggs. But when the harvester ant colony reaches a specific size, you start seeing some ants will specialize in waste removal. They'll even develop certain areas in the colony to take waste, to take deceased corpses. Certain ants will start collecting food, and we don't know why. So for a biologist, emergence that we previously described as strong or spooky emergence is very exciting, very interesting. For an engineer, it's not so exciting. I don't want extra behaviors to start happening in my system that I didn't plan for. Now, if you have any interest in complexity at all, you've already heard of Steve Wolfram's work. He began what he called a new kind of science, and his book is here. Now, what are we looking at with complexity in engineering related to our actual application? Well, first of all, it's being recognized as a problem. If you look at most systems engineering textbooks, they will simply state that complex systems can have emergent behaviors, emergent properties that we did not plan for, and that can lead to problems. Well, that's great, but that doesn't take us far enough. There have been some limited mathematical attempts to help us understand it, but it's not fully understood. And we're leading to something here at the end. Here's a few nice books on the topic. Engineering Emergence, I mentioned earlier, Emergent Behavior in Complex Systems Engineering. These give you a nice overview that's applicable to a wide range of engineering disciplines, including aerospace, systems engineering, electrical, what have you. So I highly recommend those books. And you will notice I'm very careful as I go through this. I'm not hawking any books of my own. I haven't yet authored books on this topic, although I have on other topics. There are really some good books already out there. What does all this mean for you as an engineer? We've talked about various mathematics of nonlinear dynamics and chaos theory and emergence. What does this really mean as an engineer? For a biologist, we already mentioned that this can be very exciting. You're looking forward to this. And in fact, there's a strong body of knowledge that human consciousness, your mind right now, is an emergent property from neurological interactions that are based on nonlinear dynamics. So put another way, if we didn't have nonlinear dynamics and we didn't have emergence, there's a strong body of evidence that you wouldn't be thinking, in which case you probably wouldn't be engineering and you wouldn't be interested in an engineering conversation. But for the actual engineering, it means, first of all, unpredictability. And I don't know about you, but I just flew in an airplane last night. I don't want any unpredictability in aerospace engineering. We had some hiccups in communication this morning, some sound issues. I don't like unpredictability. Divergence from requirements. I often tell students that I would define the hallmark of engineering. If you want to take all the engineering disciplines and put them together, it comes down to very careful requirements and adhering to those requirements. In fact, this semester I'm teaching a graduate course in systems integration, and I constantly harp on that. Your integration goes back to your requirements. Well, if we have unpredictability, you will have divergence from requirements you can't control. And then we'll have failure. So what does this all lead to? Wouldn't it be nice if we could predict this? Well, I've already told you it's unpredictable. I've already told you it's probabilistic. So the answer to that is you can't. Well, that's mostly true. There is a process I've worked on the past year or so that is intentionally using rather simplified math because I wanted something that could be easily applied. And what I base this on is a very simple fact that's well established in the literature. Emergence is most likely going to occur in a system where we have complexity. Where is complexity most likely to occur? In interfaces, where two things come together. Let me give you a simple example. On your automobile, what is something that fails frequently? Tires. Why? Because they're constantly connecting with the road. You might not think of that as an interface, but it is an interface. It is an interface because you have a tire that hits a road, and it's unpredictable. Why is it unpredictable? You have no idea what's on that road. The road itself, you may have a very good knowledge of how it was constructed, but there is no way to determine what objects are on that road. Simple, small bits of trash or pebbles or gravel up to large obstructions. So that interface is where we're going to have new things emerge. The interaction between my tire and a piece of glass is emergent, it wasn't planned. So how can we handle this with very simple math? Well, we're going to get to that in just a moment. That's the culmination. One of the current methods that's being used is nonlinear time series analysis. We look at a tool for complex nonlinear systems over time, but again, that doesn't give us predictability. That gives us post hoc analysis. So what do we want is a method that's simple, that anyone with even basic mathematics can do, that will give us the best way to predict emergence. So, what do? We look at a system, we look at its interfaces, and we evaluate the interface. Not every interface is equally likely to lead to complexity and emergence. We start with a simple function. We're going to look at three values of an interface. Now, I am well aware that this could be expanded upon, and I invite you to do so. But this is meant to be simple. How much data is processed through the interface? That's your beta value. How many connections to the interface? That's the alpha value. And how much variation in the information? I keep saying information. I want to tell you that I'm looking at information, in the broadest possible context. It doesn't necessarily have to be bits. When I'm driving down a road and my tire encounters a piece of glass, it's very easy to conceive of the various properties and measurements of that piece of glass as information that's now being processed at my tire's interface. So we have three values. How many connections do we have at this interface? How much information flows through that interface? And how much variation is there in that information? And I looked at information, I just simply borrowed Shannon's information entropy. That makes it very easy to follow. The beta value, we're going to look, I just chose the Simpson index, which gives you the data processed through an interface. There are a number of indices out there you could use. This is just one possibility. And then we give you a long form. Someone is asking a few questions that I am currently ignoring because it was advised to me later that my constantly answering questions breaks the flow, so I'm not ignoring your questions. I'll get to them in just a moment. If we write all this out with the Shannon index put in there, we get a long and unwieldy form, so we get a shorter form of it.
Dr. Easton, we've lost you again. If you
Any
can,
time, that takes us to the review. I just heard someone's voice pop in. If you could please put yourself on mute.
No, I'm letting you know that you disappeared for a moment. We lost your sound. If you can just go back a little bit.
Yes. Can everyone hear me okay?
We now hear you. I think you're back.
Okay. Well, let me answer a few questions that have popped up now. The gamma value is a Shannon metric, absolutely. How would you apply this to source code? I've got a lot of questions about source code, so let me address all those in one fell swoop. First of all, if you're going to look at an interface in source code, I would look at that as any function where data flows. And if you look at that as a function, and that could be a function where you connect to an outside source, such as a service, such as a database, whatever it might be, or another function feeding in, then yes, it's going to be quite easy to see the information flow because you've got parameters being passed to your function. Someone is asking, given that there are a number of theories in chaos and dynamic theory, how do you decide which one to pick for a particular problem? That's a really great question, and you're not going to like the answer. Unfortunately, one of the reasons for this presentation is I find a lot of people do have some familiarity with chaos and nonlinear dynamics, but they've narrowed down to one area, and they only know that one area, and they're not even aware there are other possibilities. So what I am trying to do, one of the goals of this presentation, is to introduce you to so many different things that you might not have seen before, and you're going to have to spend some time exploring them beyond what we could do in the space of a single 45-minute or hour-long presentation. You're going to have to spend some time interacting with these things, and then you'll be able to decide which one is applicable to your area. For example, the original Lorenz equations were designed specifically for atmospheric convection. Certainly they could be applied to other areas. Now, for those of you that are active researchers, and you're always looking, particularly faculty, for that publish or perish, I will tell you that taking mathematics that's been applied to one area and then applying it to a new area is always an excellent idea. So if you're perhaps an electrical engineer and you want to look at nonlinear dynamics that's been applied in software, that's a fantastic idea. Conversely, if you're a software person and you want to see some way to apply Lyapunov exponents to divergent behavior in software, that's an excellent idea. And in fact, one of the other questions that I'm working my way to is using this material to improve software security. Well, let me answer that more generally than just software security. Let's talk about security in general. Any system is clearly dynamic when we're talking about security. A small office network, you have the various operating systems, the hardware, the network, the routers, interfacing with the human component again. One of the first things I'd recommend, and this is for the security people and anyone else as well, apply the Lyapunov exponents and see how far your system diverges over time from its initial conditions. Then establish a Lyapunov time. What is the time within which you're able to successfully and accurately predict system performance, and when does it diverge? And from an engineering perspective, the longer your Lyapunov time is, the better. If I can make predictions about system performance today, and that doesn't matter whether it's an airplane, a computer system, biomedical implantable device, it doesn't matter. If I can make predictions today, and I can predict performance a year from now, that's a relatively stable system. If, on the other hand, my predictability breaks down within a period of minutes, I have a highly unpredictable system. how do I address that? Now, the very simplified math I just was introducing you to, what do you do with that? Well, you look at specific interfaces and you basically calculate how complex they are. The ones that have the most complexity are the ones that are most likely to lead to emergent and chaotic behavior, and therefore they get additional testing during development. Therefore, they get additional attention during maintenance. Therefore, they get additional monitoring. And that, again, if you're doing, say, aerospace engineering, and you've identified 3 particular interfaces that have the highest complexity, those might get a more frequent maintenance call than would others. If you're a security person, since I had multiple cybersecurity questions, I identify the interfaces within my network system that have the most complexity. That's where I'm most likely to have a vulnerability emerge. So let's check on those. And that is actually well validated. If you think about some of the most famous vulnerabilities, there's been several with Windows handling of server message block. Well, that's a place where the operating system is interacting with software at host and in turn interacting with the network. You've got a lot of things coming together. You have a highly complex interface. It should not be a surprise that we have emergent vulnerabilities. Now, just a few points before I open the floor for any additional questions. We've tried to answer them as we go. One, I hope you come out of this talk with some things you can apply. And I want to reiterate, it's intentional that we broadly touch on a lot of topics, and any one of which could have been deeper. There could be an entire hour-long presentation on just Lyapunov exponents or just exploring the Lorenz equations. And some of you probably have had entire lectures or conducted entire lectures on just Lorenz equations. That's a popular one with engineering professors. The idea is to make sure you're introduced to the broadest possible spectrum of nonlinear dynamics, chaos, and emergence. The final little bit of math that was given to you was intentionally simplified so that it's readily applicable into any area. Hopefully you'll find that useful. I also would invite any one of you, after this presentation is over, feel free to email me. I happily answer emails. I will tell you that I don't answer them as quickly as I'd like, but you will absolutely get an answer at some point as soon as I can. Now, with those statements made, I know we're running towards the end of our time, but there is still room for any questions. If there's any that hasn't been answered, please put them in the Q&A box. Or if an earlier question was answered, but you didn't think the answer was quite enough. Well, I'm getting a question now. And by the way, someone did ask, can everyone see these questions? No, those are just sent to me, I believe. Someone is asking about fractal structures. The idea of fractals, which are so interesting to so many people, and it's most people's first introduction to nonlinear dynamics, is literally, if I take a system that bifurcates frequently, what I'm going to get is divergence. And by having a bifurcating function that I put specific input into, as it works, you're eventually going to get a fractal diagram. It's basically a function that bifurcates frequently, and I put in input, and as it bifurcates and I graph out the function, I've built a fractal. I'm getting one person saying they lost audio. I hope that's only that one person. A few nice, kind words. Thank you very much. And a question I was hoping someone would ask. I love to end a talk on a speculative note. Normally when I deliver talks, whether they be in-class lectures, books, papers, or talks like this, I like most of my talk to be very solid science without getting speculative. But someone just asked me, how would this be applied to a machine learning training set? I have 2 answers to that. One is very hardcore science, the other is speculative. I'll give you the hardcore science first. If you want your machine learning to work and to be effective, you want predictability. One thing I have not seen done, and this is a great, great idea for a research paper for somebody, is applying Lyapunov exponents or any other measurement you like that would allow you to study over time how predictable your machine learning algorithm is. If over time it diverges too much, then you're not as predictable as you'd want to be. In other words, nonlinear dynamics can be used as a measure of the long-term efficacy of your machine learning. I haven't seen anyone do that. There may be studies out there. If you know of one, please send it to me. Now, as to the more speculative, I have a personal opinion, and I've done some limited work on the actual area of synthetic consciousness. Now, as I'm sure all of you know, unlike what the public thinks, machine learning and synthetic consciousness are not the same thing. Machine learning is algorithms that take a set of input vectors and over time produce superior output vectors. Synthetic consciousness is actually trying to get a machine to think. In my opinion, any attempt to go to synthetic consciousness that does not incorporate nonlinear dynamics is doomed to failure because our neurons have a lot of nonlinear dynamics. So those are two applications of machine learning and nonlinear dynamics and chaos. Someone is actually asking about specifically injecting emergence into AI. I don't know of anyone that's doing this now, but that's essentially what I'm recommending. If you truly want to have consciousness synthetic, you're going to have emergent properties. Now, someone has also asked about my contact information. Actually, if you just Google Chuck Eastham, you'll find me pretty quickly. My website, chuckeastham.com, or Chuck Eastham through LinkedIn will get you to my email, which can either be chuckeastham@gmail.com or chuck@chuckeastham.com. And the bottom of this slide actually has my website on it. I think that concludes our presentation and our time today. I don't know if the IEEE folks have any final statements or comments.
Yes, we do. Thank you very much for your presentation. I'm very sorry for the technical difficulties that we had, but I am glad that the fact that it could be integrated into your presentation. I think this probably is the only topic that those issues could be integrated. But thank you very much for that. I'd also like to thank all of our attendees for attending. You guys have been great. You've given some great questions. Our next Distinguished Lecturer webinar series lecture will be on the 3rd of December at 11 a.m. Eastern Time on writing professional publications and using them effectively. This will be presented by David Allen Greer, Associate Professor of Science and Technology Policy at George Washington University. We've recently added the Standards webinar series. The next in this series is the IEEE 802 Networking Standards, Connecting the World Part 1 at 11 o'clock on the 14th of December coming up. In our Build Your Career webinar series, our next webinar will be on the 17th of December at 11 a.m. Eastern Time on Solutions Thinking 101. And that'll be by Elsa Velasco-Paul, co-founder of the M&E Group. Registration is now open. We will be sending you a link to these future events along with the slides and recording of this webinar. That'll be in the email that'll come to you by tomorrow. You'll get both the slides and the recording of this webinar, as well as the links for signing up to these upcoming events. Again, Dr. Eastham, thank you very much. You were a great speaker for us today.
Well, it's my pleasure. I always love talking about these topics, and I appreciate everyone listening and bearing with technical difficulties while I got to speak about one of my favorite topics.
All right. Thank you, and have a good day, everyone.